In this video, we're going to learn about how to process signals on a computer. We'll venture into the world known as digital signal processing. Turns out that's my research area is DSP. You're going to hear me talk about DSP a lot. So we're going to start just like we did for analog signals. We're going to start talking about fundamental signals and the basic systems. And one of the points of this video is that in the digital world and the analog world, there are a lot of similarities about how you think about signals and their spectra. So we'll see that you're going to already know a lot of what I'm going to say, but there's a few little things that are a little bit different. All right, and the first thing, of course, is we're going to start with the complex exponential, our friend. This is our most important signal that we have just about. And if you recall, a discrete time signal is a function only of the integers. So we call this a digital signal. I'm being a little careful here about saying discrete time. Digital signals usually refer to discrete in time, functions of the integers, and discrete in amplitude. Well, I'm going to just talk about discrete time signals, pretending that the amplitude is a continuous valued variable. I mean, it could be any real number. It turns out that's not really true in a computer. You can't represent all numbers exactly. Everything is discrete valued, but we're going to hide that detail in the way we do our theory. All right. The first thing to note is in this complex exponential here, the frequency variable has to be dimensionless. It has no dimensions because n has no dimensions, and you cannot exponentiate anything that has units. So f is dimensionless, and furthermore, there's a very interesting property. Suppose I consider the frequency f plus an integer. So L is another integer. And if I write this as a product, e to the j 2 pi times an integer is 1. So we get that this is equal to that. That's the definition of a periodic function. So f is periodic for any integer, and of course we want to pick the smallest period. So this is periodic with a period of 1. That's very important. So every function of frequency that we're going to talk about has to be periodic with period 1 because of the dimensionless nature of f and the fact that n is an integer. We didn't have this for the analog complex exponential because t was any real number and f had to have units of inverse seconds in order for the exponent to be dimensionless. N here is dimensionless, that makes f dimensionless. All right, but this periodic behavior has a interesting consequence. So f is periodic with period 1. And it turns out, let's consider this complex exponential, which has a frequency of 1 minus f. And if you go through all the math, again, that's 1. That's the same as the complex exponential at negative frequency. So here's our f-axis. And here's 1/2 minus 1/2, 1. Let's extend it out to minus 1. So if you have some, it's got to be periodic with period 1. So that means this part looks like that. It turns out that this part, the part greater than 1/2, has to be the same as this part because it's periodic. So this is the same as that. So a frequency at 0.6, let's say, a little bit bigger than a half, according to this formula, well, that is 0.6 is, that makes this f 0.4, 0.4, which means that that's got to be the same, have the same value as minus 0.4. So the highest frequency you can have, it turns out, is a half. Because once you go above a half, that winds you up in negative frequency. So here's the name of the game. The lowest frequency sinusoid occurs at f equals 0. The highest frequency complex exponential, rather, is at a frequency of 0.5. That's the highest frequency that makes any sense. You go a little bit higher than that, you wind up back at negative frequency. So, and this highest frequency complex exponential turns out to be an alternating between plus and minus 1 forever. So, when we talk about signals that are quantities that are functions of frequency, we're either going to define them over minus a half to a half, that's a period, or we can talk about them going as a function from 0 to 1 and realizing that this part is the same as that part. This is positive frequency, this part is negative frequency in that range. That's the one difference, a very important difference between discrete time signals and analog signals. All right, let's then extend this to a sinusoid. The formula looks the same. The only difference is that n is an integer, which again makes f have no dimensions, and we're usually going to pick f to lie in that range. So the highest value of f makes any sense to talk about is half. And you get what looks like a sinusoid, but of course it's only defined as integers, so you get a stem plot. And what doesn't change, of course, is Euler's formula. So this sinusoid can be written as the real part of a e to the j phi times e to the j 2 pi fn. So again, that's the complex amplitude. That all follows through. Nothing really changes in that regard. So let's talk about some other fundamental signals. And here's our friend, the unit step. And I want to point out, I'm now defining it everywhere. You'll be happy, I guess. So here's the n-axis. I want to plot u of n. And it's 0 n less than 0, pops up to 1 at the origin, and is 1 forevermore. Okay? So that's the unit step. It's a familiar quantity. We've seen it before. Here's a new basic signal that we didn't have in the analog world called the unit sample. And this one is very simple. It is 0 basically everywhere except at the origin where it's 1. That's why it's called a unit, and it's called a unit sample because it looks like it's one value. Okay, and it's going to be written by delta of n. Okay. Now, here's the reason we talk about the unit sample. Let's sketch out here some signal, which I'm just going to call S of n. And let's assume that this is the origin, n equals 1, n equals 2, etc. Along that scale, horizontal scale there. The value of the signal at the origin is, of course, S of 0. What is the signal at the origin? Well, it's a unit sample whose amplitude is S of 0. Okay? S of 0 is just a number. So what the signal is at the origin is a unit sample. This signal, the signal at n equals 1 is s of 1 times a unit sample, which is a delayed version of the unit sample. It's delta of n minus 1, right? Because this signal is a delayed version of that, and it's delayed by 1 unit, etc. This is s of 2, s of 3, s of 4, s of 5, etc. This is s of 5 down here. So what we get is a somewhat confusing but very important formula that a signal, any signal, can be expressed is a superposition of unit samples. In fact, that's the definition of a discrete time signal. It is a superposition of unit samples whose amplitude at every sample expresses whatever the value the signal has at that delay. So this may look a little funny here, but the idea here is that the real signal is the part that depends on n. And here's the only part that depends on n in the formula. We're going to find this expression to be extremely handy a little bit later. All right, let's move on to some simple systems. And we've seen this one before, the simple amplifier, where G is the gain, of course. Well, we had to use operational amplifiers, op-amps. When we talked about analog signals that amplified. Well, now an amplifier is easy. It corresponds to a multiply. So you just kind of do it. So I've written this in kind of a computer-like code thing because that's exactly the way it works. Multiplies are very simple to do. So are delays. And time delay is simply delaying, of course, only by an integer, because all discrete time signals are defined only at the integer. It makes no sense to delay by half, for example, because we must have an integer argument in all signals. So, and a delay is also easy to implement in a computer. No real difficulty there. Also, the definition of linear systems is the same basically as it was for analog systems. Notice the change in terminology here. We say shift invariant because the delay can only be an integer. So the word shift is supposed to mean only delaying by an integer. So it's just a slight terminology change. So linear time invariant systems basically refers to an analog system. Linear shift invariant system refers to a discrete time system. So the linear part of the definition is the same as it was for analog. Superposition applies. So whenever you express an input as a sum of simpler signals, the output is equal to the superposition of the outputs that you got when you put each n alone. So nothing changes at all. And shift invariant is the same basic form as time invariant. If you delay the input by some amount, the output that you get is the original input to this when the signal wasn't delayed, and then you just delay that, and that's what the output is, no matter what delay you pick. The system doesn't change with time. And all the examples that we encountered for linear and time invariant systems apply here to the special case of discrete time. All those examples follow through. So there's really no difference here. So let's summarize the basics. That here, digital signals, discrete time signals, are functions of the integers. That has a very important consequence. We're talking about the complex exponential, things that are functions of frequency. Frequency is dimensionless and is only defined uniquely over unit length intervals. And usually it's going to be 0 to 1 or minus a half to half. and it's the minus a half to a half is the one we're going to use a lot when we're doing theory. It's going to turn out that in a practical, if you will, calculation, it's convenient to take frequency going over 0 to 1. I'll point this out when we get to it. The most intriguing thing and the simplest thing from your viewpoint is that linear signal in systems theory is exactly the same as it is for analog signals. There is no different. We have to learn anything new. So we're on our way, and now we're going to start talking about some more details, in particular the frequency domain in discrete time.